Perfect.
Perfect. Great. Go ahead, please.
All right. So no, just to sort of quickly acknowledge some of my PhD students who have done the work that you're going to see here, and some of my collaborators from Georgia Tech and France as well. Okay, so just as a quick outline, I want to start off just with providing some context for the work that I'm going to present here. And then I'm going to go through a little bit of quick background. So this talk is focused on computing and memory with like ferroelectric transistors. So I'll give just a short background about that. And we also try to apply the ferroelectric transistors in the context of associative memories, and then sort of port that to an end-to-end application study and compare it against sort of other, you know, CMOS and emerging technology-based solutions. So in that regard, like I will sort of dive deep into sort of the FEFET centric benchmarking, sort of talking about physics-based modeling, circuit design, and architectures, array level simulations, really sort of trying to emphasize what the impact of peripheral overhead might be, which is fairly substantial as it turns out, and then sort of end in an application level context. And then I'm going to close just with just a few slides on some alternative ways that we're looking at computing with these FEFET devices. There's a paper on this work that will be appearing at IDM here in a day or two. I think whenever it starts. Actually, I'm not going. My colleague is going, but we do have some new ideas with how we might use some of these FEFET-based devices, where most work is done in the current domain, and we're sort of thinking about solutions in the charge domain to improve reliability. All right. So to start, I am going to talk about like hierarchical evaluations, and I'm going to do this in the context of like an AI ML type workload, since most people are interested in that. And to be honest, if we were sort of to try to expand the scope, it would become unwieldy. So I think we'll just sort of focus on this application domain. And even in this regard, there's so many different models and algorithms that you could think about studying. Like that design space just quickly explodes as well. So I've listed three examples here, but this could easily apply to many other different models or non-AI ML workload spaces too. So to sort of make the problem a little bit tractable, like what we've done, and I'm sure other groups have done as well, is to try to identify sort of key compute kernels that are sort of universally applicable to a broad range of applications. So is it matrix vector multiplication? Is it some type of distance function? Is it a hash function? Something else, where if you could do this efficiently, there's a really good chance that it's going to be applicable to a wide variety of workloads. But then we could even ask the question, well, what architecture, for example, might be best suited for realizing the compute kernels that you see in that second row? And, then we could ask the question of like, well, is a particular technology, well suited to one of the architectures that you see in the third row? And hopefully it's pretty obvious that this design space very quickly explodes with like many, many combinations of possible technology, architecture, compute kernel, application level mappings. So if these are our incumbent solutions, like let's just pick a couple of solutions that might be useful in the context of emerging technologies with NVM, sort of these, resistive crossbar arrays have been popular for quite some time now. And then more recently, there's been work looking at like associative memory solutions to do distance functions. And it really begs the question of whether or not like these technology-driven solutions can better any of the incumbent solutions highlighted in blue. I actually want to take this talk all the way to sort of a materials level as well. And I'll come back to that at the end of the talk, where part of the funded research that I am working on actually does try to sort of answer that question. So we work with sort of material scientists, for example, in a large center level effort, and we're trying to use these application level studies to get some insight as to what device enhancement, for example, or a material centric solution might be most useful in an application context. All right, so another way to think about this design landscape, and this is a question that we get from our industrial sponsors all the time, is they kind of want to understand like what the return on investment is going to be, especially as you sort of increase the amount of disruption from the state of the art, either at the device level or the architectural level. So this is qualitative, like if a technology is missing here that you're interested in. It's not meant to be a slight or anything like that. This is sort of just a sort of a way to try to qualitatively capture this design space. And we often get asked from our industrial sponsors, especially if we're looking at a new technology or a radically different architecture, some combination of that, early on in the design process, they want to see the promise of like 100x improvement. Not really thinking that you're going to get 100x improvement at the end of the day, but as you'll see from the discussion in this talk, as you sort of start looking at more and more realistic implementations, that 100x improvement gets chipped away at and chipped away at and chipped away at. So maybe at the end of the day, we really end up with 5x or 8x or something like that. So it's worthwhile to invest in the technology. But if you're not seeing that 100x early on, then the chances of it sort of even leading to a 5x or an 8x improvement are pretty slim. So in this talk, I'm going to sort of talk about these four boxes, sort of looking at FE-FET-centric solutions for ML AI type workload in the context of computing in memory, just using the memory technology as a conventional random access memory, and then also sort of comparing to like incumbent CPU or GPU solutions too. I should add, you could almost imagine, we've had some discussions about this in the context of our research programs, of adding a whole other axis to this graph, where I think there is growing interest, for example, in like heterogeneous integration solutions, where maybe, for example, just better packaging, for example, might also sort of lead to some interesting performance gains using incumbent technologies. So that's something that is on our radar, but I haven't done much with yet as of this point. Okay, so I'm going to focus on this memory augmented neural network workload in this particular presentation. We actually are sort of porting the analysis that you're going to see here to like recommendation system workloads and transformer workloads. We actually just submitted a paper on the latter. But I think that in the interest of sort of telling a complete story, it sort of makes sense to look at this box here. Okay, so if you're not familiar with ferroelectric field effect transistors, I've just got like a 1 or a 2 slide tutorial here. Basically, what we're doing is we're integrating ferroelectric material into the gate stack of a transistor. And to simplify the discussion, what this really allows us to do is dynamically shift the threshold voltage of the device. So you could make it high, you could make it low. The difference between sort of this high and low voltage we can consider to be a memory window, and we have the ability to sort of store information locally within the transistor itself, and it can function as a memory. Now, that all sounds fine and good. I'll, right up front, sort of the two downsides to this device is that energetically, writes can be pretty expensive and time consuming as well. So it's not something you can update frequently. And the other challenge here is that there could be an endurance issue. So the more times that you write the device, like the more likely it is to wear out. We certainly don't have an infinite endurance probably to work with. Other challenges, which I'll touch on a little bit later in the context of some of the benchmarking work, is that as we are writing these devices, let's say in some compute and memory array, like disturbance issues are real. And you have to consider, for example, like inhibit voltage schemes, for example, to ensure that you don't inadvertently change the device state, for example, in an adjacent row or column. And that actually can sort of further exacerbate some of the peripheral circuitry overhead, which will ultimately impact application level performance metrics too. So again, the study that we'll look at is done in the context of content addressable memories. And we've considered sort of different types of content addressable memories in the context of FE-FET and other technologies as well. So just a, one slide review of this, with, sorry about that. Let's say that I wanted to sort of search for the pattern 0, 1, 0. So in this particular case, this is obviously not a match because each bit, for example, is the complement of the other. But in this particular instance, we would have a match because the 1 and the 0 match here, and we're storing a don't care state, which can be treated as a 1 or a 0 match, regardless of what is applied at the input. We've studied multi-bit associative memories, leveraging some of these ferroelectric devices where instead of just encoding a 0 or a 1, you might encode multiple states. So this is an example with, say, state 1, state 2, and state 4. So in this case, you would see again the match in the top row. And there's interesting work from some of my former PhD students actually over in China and then other colleagues at HP Labs, for example, that have proposed this idea of an analog content addressable memory, where it's possible to store ranges of data. And then as long as you're searching for any bit of information within that range, it would be treated as a match as well. This is a really neat idea, I think. From our simulations and practice, like you can sort of get into a lot of sort of edge cases where, you have sort of a pathological match, but ends up sort of like giving a false result. I won't go into the details of that. So I think that this is practical up to, maybe 3, maybe 4 bits. I think this is challenging unless your application is inherently tolerant of some, false positives or false negatives. So the other thing that I should mention is that a lot of times with these associative memories, we can get some unique matching functionality. So for example, we might sort of do like a true exact match. We might go ahead and implement like a best match. So just find the row, for example, that has the most matches, which are green squares. Or we might even sort of think about like a threshold match. So return all of the rows, for example, that have, fewer than 2 matches, or 2 or fewer matches, I should say, in this example. So that can also be useful in the context of an application or an algorithm. This slide is again sort of purely qualitative, but what I tried to do a little while ago is sort of just look at the scan the literature to see sort of what applications are using different types of associative memories. And moreover, like, are they looking at a specific technology? Are they technology agnostic? And sort of trying to highlight columns of data. You can see that here sort of we're just using sort of a traditional like binary CAM functionality here. This is a ternary CAM functionality. And just sort of looking at what functionality might be required for a given application. So if you were interested in, say, doing like a bioinformatics problem or a transformer workload to accelerate like a scaled dot product attention, like what CAM functionality might actually be useful, or what are people studying at this point in time. So I won't come back to this, but like I think that there is sort of different CAM functionality that might be required or would be ideal for given workload types. All right. So now I want to just sort of quickly introduce this like memory augmented neural network problem, which will be the basis for some of the analysis that we're going to do. So if we think about how like a memory augmented neural network might work, is we could start off with a trained, let's say, CNN network in order to do some image classification problems. So let's say that we had, trained this network to identify 100 different classes of animals. And normally what we would do is we would take these, output neuron values, feed them to a softmax function, get a probability distribution, and so on. But here what we're doing is we're actually just storing the real values in like a vector. So basically treat it as a feature vector that's associated with a given class. So then what I might do is I could provide a new query to this particular network. So in this case, I'm showing it a different picture of a rabbit. I would generate that feature vector, and then I might go ahead and just do a comparison of every learned feature vector to the feature vector that I just generated. And I can sort of try to figure out what the best match might be by using some distance function. In this example, it's a cosine distance function, for example. So then an advantage of this is that post-training, we could go ahead and show the network new classes that it had seen before, generate new feature vectors, store them inside of the network's memory. And then if we sort of show that network a new example of a new class that it didn't initially learn, then we could still provide some insight into a meaningful inference, for example. Now, in terms of how we might map this to technology, well, one thought is to go ahead and take sort of the real valued feature vectors, and you could use like a hash function, for example, to generate a binary signature that's sort of based on those feature vector values, store them in a memory, and then you could sort of do a search just using like a binary content addressable memory, for example, and do some matching function like I showed earlier. Well, one of the things that we observed by looking at some of these ferroelectric associative memories is, again, we have the ability to represent multiple states of information. So we don't just need a low threshold voltage and a high threshold voltage, but we could sort of think about something that's in between. And in this particular case, we could take our real valued feature vector values and then quantize them to a multi-bit state and treat that as a feature vector. And what's interesting about this idea is that if we were to use sort of these ferroelectric devices to implement a multi-bit associative memory, the the current that we see um, in the this is a 2 FE associative memory cell, basically, has sort of this quadratic relationship between the stored value and the query value, right? So imagine, for example, that there was a perfect match between what was stored in the multi-bit FEFET CAM cell and the query value. In that particular case, the conductance of the cell is relatively low, and like your match line might stay charged. But as the query starts to deviate from the stored value, the conductance has sort of this quadratic relationship in either direction. I'll sort of just draw it in one direction there. And what we can actually do is we can leverage that to mimic like a Euclidean distance function, for example. So imagine, for example, that my stored value is mi, and then my query value is qi. And in that particular case, this would sort of be stored in the associative memory, and then we would sort of search with this particular value. Just in a sort of the mathematical expression for Euclidean distance, we're looking at sort of the difference between those values, and we take the square of it. And it turns out that if you look in the literature, you can use sort of just Euclidean squared distance as a proxy for Euclidean distance, so we don't have to worry about the square root necessarily. All right, so that cell conductance basically computes, if you will, the qi minus mi squared term. And if we sort of combine sort of multiple associative memory cells on a common match line, this kind of mimics sort of the summation function. So we can kind of mimic this Euclidean distance function inside of the memory, and we don't have to transfer data, for example, to another functional unit in order to do a particular computation. So effectively, what we're trying to do is implement a more sophisticated distance function, say via like instead of Hamming distance, do something like Euclidean distance function, which algorithmically is more useful, mimicking that in the memory. All right, so again, I'm trying to move away, to be quite honest, from this memory augmented neural network problem. This is something that we studied for a few years, and I still sort of use this as a case study, and I still have some students collect data on this problem because there's been a lot of work in the literature about technology-enabled solutions for it. So we can make some, I think, interesting comparisons. So these are 4 examples that look at the same exact few-shot learning problem with a memory-augmented neural network. So basically using this omniglot data set, showing some number of examples of new classes, sorry about that, that it hasn't seen before, providing a new query and seeing if we can find sort of the best match. So we've looked at ferroelectric solutions. There's been work with mapping the values to hyperdimensional spaces from IBM. Some colleagues in HKU have looked at complete end-to-end RM solutions and so on. So I want to talk about that a little bit more here. So if you think about sort of this memory augmented neural network problem, there's really 3 main steps that you could consider. And the first is the encoding. And that's basically, thinking about what neural network you're using in order to generate the feature vector over here. And I'm not going to read every last, detail here, but here, for example, this is done on a GPU. This is also done on a GPU with the same precision. Here, more features are used than over here, and that can impact the classification accuracy. Here, this is all done end-to-end in RAM, actually on actual RAM-based crossbar arrays. So, we're changing the technology from CMOS GPU to an RM crossbar here. And then it's a question of what you do with the feature vectors that you learned. So here they're hashed to binary signatures. The work that I just talked about sort of considers quantization to multi-bit signatures, and I'm going to exploit that idea in some additional analysis here. This work considers mapping those feature vectors to a hyperdimensional space, and we'll actually try to combine these ideas going forward. And then this work just sort of looks at, again, sort of mapping to binary signatures. And then the question of how the distance function is performed is also different in each approach. So here we're using Hamming distance. Here, this is Euclidean distance. Here, this is a cosine distance approximation. Here, this is Hamming distance again. So different approaches are trying to sort of do the different steps of the algorithm in different ways. So we've kind of fundamentally changed the underlying algorithm, which is useful if it maps well to the technology, but it makes it challenging to actually do the evaluation because there's a lot of underlying assumptions that we have to try to reconcile. So this chart, there's a lot going on here, and I'll try to sort of explain it piece by piece. But what I try to do is use accuracy as kind of an initial sort of first filter for whether or not a technology-enabled solution might be good. Right. So this is again sort of just the four approaches that you saw on the previous slide on the x-axis here. And then the classification accuracy for a given problem is on the y-axis. And the colors here basically represent blue is just the pure CMOS CPU, GPU solution. Green incorporates some technology. You might still be doing the encoding on a GPU, but maybe you're doing the matching with an FE-FET associative memory. And red is all experimental. And then the shape of the data point represents the attention mechanism that's been used. And then I've tried to annotate every data point with the precision of the encoder and the matching function. And then also if there's any variation that's included as well. So then rather than trying to sort of talk about this graph all at once, I'm just going to call out four major trends that we observed by studying this data. The first is shockingly, sarcasm intended, is that the higher precision GPU is going to give you the best accuracy. So there's really not a surprise there necessarily. However, most of the work with GPU solutions just inherently assumed cosine distance. And what we saw is with proper training, the Euclidean distance basically was almost on par with the cosine distance. So we think that these can be somewhat interchangeable, if you will. If you look at sort of an all experimental approach, you seemingly see like a almost 5% drop in accuracy. But again, we're sort of changing multiple things here at the same time. Here, the precision noticeably is lower. Again, this is sort of all done on an experimental basis. So like this is, going to account for some, new memory technology variations and so on. So we really want to try to understand like what's, causing that drop. And then as the variation increases, again, not surprisingly, you're seeing a negative impact on classification accuracy. But we think we can kind of use a chart like this in some sense to, try to get some insight as to what device characteristics might be acceptable. So if I'm a customer, for example, I can say, I have to have an accuracy that's above a certain threshold. And if I'm not, then I can eliminate the solutions that are sort of below that data point. All right, so we think that some of these FE-FET associative memories can actually get us up into the space that you see up here, and I'm going to talk about what they would have to look like for that to happen. All right, so this chart, again, a lot going on here, but I'm going to try to pull together a lot of ideas in sort of one slide. So the first thing that I'll draw your attention to are these vertical lines that are shown here. And these just sort of capture some of the peak accuracy values from the solutions that you saw on the prior slide. So you can almost think about these vertical lines as targets that we might want to hit. Like this is an all GPU solution where we're using Euclidean distance. This is work from IBM that sort of maps the feature vectors to a hyperdimensional space, but using a high precision. This is work from IBM that does the same thing, but then sort of just looks at one bit or vectors with just one bit elements, for example, and so on. So that's sort of some baselines that we want to try to compare against. And then the curves that you see here that are highlighted in blue basically try to use the multi-bit associative memory doing a Euclidean distance function at that cell level in order to think about whether or not we can match the accuracy of our target solutions. And we sort of assume either 3-bit precision or a 4-bit precision here. So the other thing that I should note is that we're actually looking at the accuracy as a function of the sigma of variation in our target threshold voltage. So imagine, for example, that I wanted to sort of set an FE-FET threshold voltage in a particular to a particular value to represent a particular state. Like, there may be some variation, for example, in the threshold voltage that I actually get for a given device. So this is going to try to capture what the impact on stochasticity is in terms of accuracy for this application. So we actually have some data along these lines. This is collected by collaborators at Fraunhofer IPMS on somewhat larger FEFET devices that they had access to. And if we look at this, we can see sort of to set a device into sort of one of 8 different states, we see a sigma of variation of 128 millivolts. And this is kind of a somewhat limited write and verify scheme, like the way that this was set up. Like if you exceeded a particular target threshold voltage, you actually couldn't reset it to go back. So this is a little pessimistic, but it's a data point as to where we might be right now. And what's interesting is we can then go ahead and say, well, if I have that sigma of variation, well, that means at best that I'm losing, almost 2% in accuracy basically from a baseline. So like I'm no longer ISO accuracy in this particular case. So it begs the question of whether or not we can get to like a higher accuracy, in the future, and what the device would have to look like in order to do that. So we studied that question. And in this case, we leveraged some physics-based simulation models from our collaborator Kai Ni, where we can actually look at an FEFET device, consider the number of ferroelectric domains that might be associated with that device as it scales down or up, if you will, and then also what the sigma of variation might be if we attempted to sort of set the device into a particular state. And in this case, we used like a write verify scheme where we try to set the device state 10 times. If we fail after the 10th time, we just kind of live with what we have. So there will be some error basically in the data that you're saving for your memory augmented neural network feature vector. And the way to interpret this would be to say, let's say that I wanted to hit this particular accuracy target or this particular accuracy target. I can use this chart to say, and understand like what sigma of variation I would have to have from my device in order to achieve this target. And if we assume that a domain size is about 10 by 10 nanometers, you can say, well, if I want to hit this 61 millivolt target, then it gives me some sense as to how much I can actually scale this device. All right. So yes, I may have this sort of like more functional multi-bit associative memory, but its device size can't go below 100 by 100 nanometers. Otherwise, the variation will be too high. Or if I wanted to hit this higher accuracy target here, then my device size might have to get even larger. So this kind of gives us some sense as to where we could go or where we might have to go from a technology standpoint for this to be useful in an application level context. All right, so that's accuracy. What I want to talk about now actually is energy. So again, sort of looking at some target accuracy baselines. So these, dashed lines and dotted lines you see here, those are just copying over those vertical lines from the prior slide. And now what we're looking at is sort of the accuracy with write verify. But we also sort of looked at what would happen if we didn't use a write verify scheme. And you can see that as the device size scales down, if we're not using write verify, the device stochasticity is pretty bad. So, you're losing more than 10% in accuracy for this particular problem if you're not sort of checking the state of your device after you write it. Now, then it begs the question, like what happens with search energy? And search energy is going to be identical whether or not you use write verify or no write verify, because you're just searching your associative memory in parallel, and whether or not you're reading the wrong data or more accurate data doesn't really matter. Search energy is going to be fixed. But the write energy is actually a more interesting question to study. So imagine, for example, that I wanted to use this write verify programming scheme. And again, I'm going to sort of cap the number of attempts that I have at 10. So I might go ahead and start setting the device with this train of pulses. And each time I sort of apply a pulse, I'm going to check its state, check its state, check its state. And if I overshoot, then I could apply like a negative voltage pulse, for example, to try to reset the device to keep programming it. And what I did is I annotated this chart with the number on average of set events and reset events that are required in order to sort of hit the accuracy values that you see here as the device scales down. And this may seem a little bit counterintuitive because you're like, well, the energy consumption is actually lower for doing sort of more reset events, for example, than you would see up here. But what's actually happening here is these devices are so big compared to, say, the devices that you see here, that the overall array parasitics and so on start to outweigh the number of write events that you actually do. So this is just a function of the much, much larger array size given the much, much larger device size. All right, so we use this study to sort of try to understand like what trade-offs might be with respect to, say, accuracy. So if I were, for example, to forego write and verify, let's look at this 150 domain device. Well, I'm going to lose almost 6% in accuracy. Sorry about that. I don't know why my computer keeps advancing itself. Um, but I'm going to gain almost 8x in terms of write energy. So there's a trade-off to be had there. And maybe I could improve that a little bit if I'm willing to, if I want to improve my accuracy loss, let's say to just about 3%, I can still get a 6x energy savings. However, I pay the cost of a slightly larger device in order to get that because I have to go to a device that has more domains. So these charts were generated for some of our industrial sponsors who kind of wanted to see like what the landscape might be, with the motivation being that, different clients might have different demands that are acceptable with respect to accuracy, energy targets, scaling targets, for example, that they might want to hit. Just kind of meant to show the trade-offs that you can see. But this actually is not the whole picture. So two other ideas that I want to introduce sort of in the next like last 15 minutes or so maybe is we did as a thought exercise, what would happen if we just use these FEFET devices as a conventional random access memory? I'm actually not advocating for that at all because I think the endurance issue will be a real challenge, but it's kind of an interesting thought exercise. And immediately we can see that even if we sort of highly scale the device to, let's say, 20 domains, uh, we can't get to ISO accuracy with a 2-bit or 3-bit or even a 1-bit device unless we use a write verify approach. And if we wanted to sort of think about using the device as a multi-bit memory, so sort of storing states 0, 0, 0, 1, 1, 0, and 1, 1, we would have to increase the size of the device in order to get sort of in this range again. So just looking at FEFET solutions alone, treating it as a random access memory or leveraging sort of this multi-bit associative memory functionality, at best, this is kind of the takeaway that you would see. All right. So if we use the multi-bit associative memory, we lose area, but we do gain almost an order of magnitude in terms of energy because we're not actually sending the data to do the distance calculation to some other functional unit. That distance calculation is being done in situ in the memory itself. So you could say that this is sort of a Pareto optimal design, but you are giving up area, if you will, with respect to a completely random access memory solution. Now, what I'm about to describe is basically going to obviate this as a valid design point. Like it's not going to be Pareto optimal anymore once you go ahead and consider the peripherals compared to a CMOS memory solution. All right, so that's the takeaway that's coming here. So real quick, like comparing FEFET MCAM to sort of an FEFET conventional memory, that prior analysis did not consider things like peripherals in either instance. So now let's go ahead and do that. So I'm not going to go into the details of this, but here are some of the overheads that we need to practically consider. If we wanted to have a negative voltage, say to do a reset pulse, we would have to consider, isolated N wells. We actually opted for a body biasing scheme to sort of remove this requirement. But the caveat there is that you sort of still need these high oxide or thick oxide transistors, which are larger. You need level shifters to operate them, so on. That's going to introduce area overhead. And just pictorially, you see something that looks like this, where if this is your actual FEFET memory array, like all the other stuff around it is the circuitry that you need to properly operate that particular array. All right, so the area is going to go up somewhat substantially. All right, so what we tried to do is we scaled this down to sort of an advanced technology node using a slightly larger PDK for the layout work that you see here. And I'll try to quantify what those overheads actually look like in an application context next. All right, so now we're considering, the fact that we have to generate a query with 8 different voltage levels, peripheral circuitry overhead, word line drivers, and so on. All right. So here's the sort of the numerical takeaways. If we consider a FEFET array, let's say that we have a device that has 100 domains that's associated with it. Like this is roughly on par with a CMOS, like SRAM based memory at the 22 nanometer technology node. So if we were to consider a solution where we stored our feature vectors in 22 nanometer CMOS SRAM, then the area and the search energy for that CMOS SRAM would be up here, and the area and the energy for our MCAM solution using write and verify or no write and verify, note the much larger device, would be over here. So you could get some energy savings. It also looks like you get area savings. And again, you could get some energy savings, and it looks like you get area savings as well. This is actually not a fair comparison because, we're well beyond the 22 nanometer node for CMOS. So we said, well, what happens if we just scale to the 5 nanometer node? Even that's probably a little bit, like optimistic, if you will, for the FarrowFed solution. But our sponsors were happy sort of with this comparison. And now what you look at is the FEFET solution is in fact more energy efficient than the CMOS solution, but it is not as area efficient because of the fact that you have sort of these larger FEFET devices that you have to have if we wanted to sort of consider ISO accuracy solutions for the problem at hand. Now, what happens if we go back to our FEFET solution where we just consider this as a random access memory? Well, in that particular case, if we compare it to this FEFET in-memory computing solution, there's a substantial energy loss, and there's also an area loss as well, because we still need some peripheral circuitry to support the write verify operations. And if you compare, let's say, a 1-bit FEFET memory, highly scaled, to a 1-bit CMOS memory, again, substantial area losses and also a nominal energy loss as well. So effectively, like these two design points, don't sit anywhere on this Pareto frontier. And this is kind of just not a good way to use this device. Like we need to do something else with it, perhaps via some like compute and memory functionality. All right, so going back to sort of the chart that I started off with, let me sort of just share where these data points might fit. So this is our associative memory in-memory computing solution. And then these would be our solutions where we store our feature vectors in an FEFET memory and we transfer them to a GPU to do the distance function calculation. So in that sense, the FEFET MCAM solution is advantageous. You're saving energy, you're saving area. However, if you add in the CMOS data point, there's no advantage whatsoever by backing your compute unit with a potentially denser or non-volatile, for example, or multi-bit ferroelectric-based memory. But if you compare the compute and memory solution to the CMOS solution, you do in fact save almost an order of magnitude in energy with a nominal area loss. So can we do better? I said that I would try to tie this. Oh, there's other data points that we could consider here too. So can we do better? So this is kind of a thought exercise where if we wanted to provide some feedback to our material scientist collaborators, what could we do in order to potentially improve the performance of the FEFET associative memory solution? So let me go ahead and highlight a few data points here. These were the numbers where we assumed a 500 domain device, no write and verify. It wasn't even ISO accuracy, but at least it looks like Pareto optimal sort of versus the CMOS data points that you saw earlier. However, if we go ahead and introduce the write verify approach, this is also now ISO accuracy, and you still have some energy savings, albeit with some area loss, but this would be sort of Pareto optimal. So then the question that we asked ourselves is, well, what could we do to try to get out into this corner over here? Would it be better to sort of use write verify and scale the devices more? Or would it be better to reduce the device stochasticity so you wouldn't have to use a write verify solution? And I'll just highlight a couple of data points here. If we were to go ahead and scale the device to, let's say, 50 or 20 domains, assuming that we could sort of get to ISO accuracy with that solution, the energy and area savings are actually not really all that substantial. However, if we didn't scale the device at all, and we could actually go ahead and eliminate a lot of the overhead of that right verify circuitry, then you're sort of getting those energy improvements, and you're almost ISO area, for example, with the CMOS solution. So long story short, and takeaway to the my colleagues sort of who are doing work at the material science and device level, like scaling is actually less important in this case than having a more deterministic write process to eliminate a lot of that peripheral overhead. All right. So I'm going to take like 3 or 4 more minutes, if that's okay, and then I'll leave the last 10 minutes for questions and just sort of highlight one future direction that we're looking at. So as you've seen, sort of a challenge to sort of this deployable compute and memory solution using an FEFET-centric solution is that we're doing computation in the current domain, and this is highly subject to variations of the device threshold voltage. So if we wanted to sort of think about more sophisticated workloads, is there a better way to use these devices? So one approach that my colleagues and I have started to look at is kind of a more like DRAM-like compute and memory solution. We call this 1FE FET1C. And in this particular instance, we actually use the ferrofet as an access transistor, and we can sort of selectively charge and discharge this capacitor. All right, so it's kind of like DRAM-like in this particular context. So the way that computation would happen is you're basically computing via charge sharing, right? So you can sort of selectively charge and discharge this capacitor, and then sort of consider the aggregate charge, for example, on the bit lines that you might see here. So in this particular case, this might minimize some of the disturbance issues that you saw earlier. So I'll just do two quick examples. These are some animations that one of my actually previous PhD students, now postdoc, made for me the other day. Is you can actually operate this 1FE1C solution in different modes. So you can consider it as a traditional random access memory, DRAM-like, if you will. But at the same time, information would be stored in the polarization state of an FEFET. So like it would be non-volatile in that sense, and you wouldn't have to do refresh operations. So the way that you might read this data is you could imagine applying a voltage, for example, that would turn on devices in a logical 1 state, but would not turn on devices in a logical 0 state. And what would happen is that capacitor in the device storing a 1 would be charged, and the capacitor in the device that stores a 0 would not be charged. And then in step 2, we can apply a higher voltage. Again, it's going to turn on both transistors, and then we would simply sort of discharge the capacitor back through the FEFET, or if there's no charge here, that would be, no charge movement. So you can sense your 0 or your 1 in that case. The other thing that you can do with this is you can do a MAC operation, for example. So imagine that I'm storing the pattern 0011. So here in step 1, I might go ahead and search for or apply input zeros. So I would apply a voltage, for example, that's in this regime, so below the threshold voltage for 1 and 0. And in this particular case, neither of these capacitors are charged. And then we apply a voltage that's associated with an input 1. And in this particular case, because we have an input that's a 1 and we're storing a 1, then the capacitor associated with this cell is charged. Finally, in step 2, we simply sort of do charge sharing, for example, and we could sort of sense the number of capacitors that are charged. So the whole notion here is this is a little bit more forgiving to threshold voltage variation in your FEFET. As long as you provide enough time, that capacitor is going to get charged up, if you will. And you can sort of do computation in that way. I won't go through the details of this slide. I'll sort of just put this all up here, but you can do ternary content addressable memory functionality with this as well. The only caveat being is that you have to sort of store your data column-wise instead of row-wise, like let's say for a random access memory. So we're still sort of working out some of the implications of that, but we're trying to work on using this approach to consider functionalities that are associated with sort of more advanced like ML AI type workloads. And that some of that work has just been submitted and is under review. So I'm going to stop here. I know that I think we end at 11:30, so I'll stop here, and I'm happy to take any questions that people might have. And thanks for the chance to speak and your attention.
Thank you very much, Michael, for the very nice presentation. I'm gonna stop the recording.